Hello and welcome back to the Drive School. Today we are going to look closer on the DC converter. The DC to DC converter is a relatively new product from Danfoss VACON. The DC-DC converter can adapt any energy source that fits into a quite wide voltage window into a common DC bus system with a fixed DC voltage. Typically usage is peak shaving in a common DC bus system, where you have to adapt the voltage on a common DC bus to the battery or any energy source that you have selected. The DC to DC converter is bidirectional. That means you can decide which direction the power is supposed to float. Typically, it's installed in a system where you have an AC grid powering a heavy consumer. And power peak shaving is then on the DC bus system. One of the advantages with a DC to DC converter is not only to utilize an energy source with a wide voltage window. Also, you can utilize a quite high DC voltage, which ensure a high AC voltage on the consumers. Motors for ship propellers and heavy consumers are quite dependent on the maximum highest voltage, and the voltage drop as function of state of charge will then not be seen on the consumers. However, be aware that to keep a constant kilowatt on your consumer side, when the voltage drops off on the energy source, of course the amperes have to go up to supply the same kilowatt. Battery driven consumers, that could be a battery ferry, or it also could be as uninterruptible power source when the ship have blacked out and there is no power available from the generators. Then you can power your heavy consumers from the energy source, and you can do this totally independent on the ship grid. You can even power up from black ship. Here we have the small energy storage, which is not connected to any cables, nothing. It's only a battery of about 400 volts. And we are now going to create a 795 volt common DC bus system. After the pre-charge, the battery voltage is seen here, 440 volts. When it starts, it actually generates 795 volts out of this battery of 420 volts. Here on these plugs, the common DC bus consumers now could have been powered bidirectional from the battery energy source. This is now an energy source for a battery driven ship. You don't need any AC grid to supply your consumers, so this is now a battery driven ferry or a vehicle. We are now going to look into how the DC converter works. How can we connect a common DC bus system of 750 volts to a battery of only 440 volts? And also we use the IGBT side. Normally the motor is connected to this side, and we actually power a battery. And we do all this with a regular frequency converter straight out of the shelf. The only thing special with this drive is that the software inside is for the DC converter, and we have added some few components on the motor cable side. To use our regular frequency converter to produce DC, we have to add these three chokes, one for each motor phase. They are connected together in one point and connected to the plus. It's important that these chokes doesn't have the same iron core, so this must be individual chokes. The minus side of the battery is connected back to the DC link minus. On our model we can see this. The motor cable is connected to these chokes, and via a pre-charge to the plus of the battery. The minus of the battery go directly back to the DC common bus. The allowed voltage window on the battery is limited in the maximum voltage to be about 20 volts, 30 volts below the common DC bus system. The reason for this is the freewheeling diodes in the frequency converter. These blocking diodes will block the 750 volt from flowing into the battery. However, for the battery voltage, it needs to be lower than 750 with some safety margin. Otherwise, the current will flow uncontrolled through the freewheeling diodes and into the common DC bus system. Now that we have connected the shocks to the motor cable side, how can the frequency converter produce a DC voltage to a battery? This thing is designed originally for making AC voltage to a motor. The way the DC converter works is by sourcing current through its IGBTs with pulse width modulation. The three motor phases are summarized in this point, going to the plus of the battery. The current in each phase have a trapeze-shaped waveform. The pulse width modulation making this trapeze-shaped waveform is about 5 kHz. The three motor phases are separated about 120 degrees, and the summarization point, this point, the current will be the sum of the motor phases. When we want the current to flow from the common DC bus to the battery, the higher voltage on the common DC bus will drive this current. The IGBTs will, with pulse width modulation, source the trapeze-shaped current into the shocks. The summarization of currents will go to the battery, and the minus is led back to the common DC bus minus. What about current flowing from the battery to the common DC bus? The voltage level here is higher than the battery, so this should seem to be a little bit complicated. What we do is called DC boosting. We are boosting the voltage over the shocks in such a way that we can have the current flowing in this direction. What happened with DC boosting is that we set up a small current through the shocks. We saturate the iron, and then we cut off the current. We connect these IGBTs, so this potential is the same as this potential. The current is then stopped quite abruptly, and the voltage will increase quite rapidly over the shocks. So we are boosting the DC voltage level here. The DC voltage level then will be higher than the common DC bus, and the current then will start flowing through the freewheeling diodes on the frequency converter. By manipulating the shocks with this DC boosting, we then create a current coming from the battery into the freewheeling diodes and into the common DC bus system. It's a quite impressive way of creating a current that looks like we are going from a lower voltage level to a higher voltage level. The way we produce the current from interleaving these trapeze-shaped motor phase currents will result in a current that have some small ripples. The size of these ripples will be determined by the size of the shocks, and also, if needed, if we utilize a capacitor between the plus and the minus. The impedance for high frequency will be lower in the capacitor than for the batteries, so the high frequency will be sourced through the capacitor then. Dimensioning the shocks are done individually for each and every project by Danfoss and VACON specialists. The reason why there is a need for customization is that the voltage window for the battery and also the current requirement can be quite different from each and every project. The need for DC boosting can be different. Also, the ripple requirement for the battery could be quite different. So the need for the capacitor also is a part of the dimensioning. Now that we have seen how the DC converter works, how to control it. You can control it in two modes. One is voltage reference mode and the other one is in current reference mode. When you run it in voltage reference mode, you basically aim to produce this common DC bus voltage. You also have a drooping involved so that you can share the load with other energy producers like an active front-end. Running in current reference mode is different. Then you basically just adapt to the DC voltage on the common DC bus. However, you have like a power handle for current to the battery. You can decide like on a power handle for the current going into the battery or out of the battery. This is useful where you want to charge the battery controlled, and also when you have an energy storage system where you want to override the whole system from your power management system. To connect the battery to the drive when the drive is not charged, we have to be aware that this huge capacitor is like a short circuit for an abrupt voltage rise. We should, when we connect the battery to the motor cables, we should connect it via resistor. This will be a pre-charging, very slow current flowing into the capacitor, and the voltage will rise very nicely. When the drive says it's ready, it will, with its digital output, connect this relay and override the resistor. So when we run after the pre-charge, we run over this contactor. We have now seen how the DC converter works. In the next sessions we will take a look at parameters and also how to control the DC converter from the power management system. Thank you for watching.